Let's first look at extension 1, calculating the frequency using maximize min divided by 2. So let's come over here. Because this is a digital device and it gave us no decimal place, the uncertainty could be 1 hertz. That's okay, but we're going to find out a much better way to do it. And many of you can already do this. It's max minus min divided by 2, so equals, open brackets, then I hit max. I can click the word max, and I can click that, close brackets, minus min. I don't need to, I can click it, or I can just go open bracket, the same as clicking it. I go close bracket. Then I go close bracket again, divide by 2. These first and last brackets, or they have this whole thing over a fraction, divide by 2, enter, fail down. Now what this shows us is we have the average value, and with the average, some things are higher, some things are lower than the average. With the average, we've got a plus and minus. That's why it's a range divided by 2. This particular one has the highest uncertainty because this data is quite low, and that one's quite high, so it has the highest uncertainty. And we're going to see that on our graph. So that's first off the extension 1. Now extension 2, add a column to your spreadsheet for wavelength and use a formula to calculate it. Use the theory above, where if you look up here, length is 1/4 the wavelength. So wavelength will be 4 times the length. Let's do that. I'm just going to copy this to be quicker. We have a nice heading. Boom. Now wavelength is 4 times the length, so it's going to be 4 times. I could write 12, and I could write 5 times 4 is 20. I could do that, but I'm not going to. Instead, of course, equals this times 4, fail down, yes. Awesome. Let's delete that because we don't know that yet. Let's go back to our lovely instructions. The uncertainty in the wavelength is 4 times the uncertainty in length. Okay, the uncertainty in length was 1 millimeter or 0.1 centimeters. So uncertainty in wavelength is 4 times it because we're 4 times in the length. So also 4 times the uncertainty, so we plus or minus 0.4 centimeters. Again, I need to match the decimal places here, so I'm going to increase this to 1 decimal place. Perfect. Now we're making a graph in Logger Pro. Now we're going to make a graph in Logger Pro. We're going to have the wavelength be on the x-axis and the average frequency be on the y-axis. So let's copy just the numbers into Logger Pro. And I'm going to double click here on X. I'm going to call this wavelength. And the short name, Logger Pro is so awesome. I'm going to Greek lower alphabet. I'm going to search here for lambda. It has it for me. And our units are centimeters. Done. Go over here to our average frequency. I'm going to copy that. Double click on Y. Frequency F, and my units for this are hertz. So we have our general graph shape. Now we need to add some uncertainty. So I'll double click back up here. I click on options, error bar calculations, and the uncertainty for wavelength is remember 0.4 centimeters. So it's going to be 0.4 centimeters. And we get these little error bars. Perfect. To get the uncertainty in frequency, I'm going to make this graph a little narrower. Make this table a little wider. Say insert, data, new manual column. I'm going to call this column uncertainty in frequency. I call this delta F. Mac users, remember delta is option J, but if you're a Windows user, you can just come here, go Greek upper, and, or is it lower? I don't see it. Oh, it's right here. Obviously. Delta F. And our units for this, remember, are hertz, because it's uncertainty in frequency. And we're going to copy and paste in this here. We get that. Now, for the uncertainty frequency, I'm going to double click up here on F. I'm going to go to Options, Error Bar Calculations. Instead of a constant, we're going to use a column. And we're going to use a column uncertainty in frequency. That makes sense. And it gives us these error bars. So remember, we have some that are big. That's like an 11. This is a 1. That's a 13. This is a huge 24. But each one of these ticks is 100, so it still looks small. That's how we get the error bars for both wavelength and frequency on our graph. Logger Pro asks us, or the instructions ask us, to choose the inverse relationship in Logger Pro because that's a relation between velocity and frequency and wavelength with our formula V equals F lambda. So I'm going to go to Logger Pro. I'm going to go here on the graph. I'm going to choose inverse, because that's the kind of relationship it is. Try fit. And here, it's not bad, but it's not great either. What I found out with some deeper analysis, and because I know what things should be like, I figured out my first 2 points were not good points. So I said I'm going to drag this little thing here. I'm going to drag this to the right. And now these data match a lot better. I also know I want a number for the A value around maybe 340, 330 in that area. So I want to get a value closer like that, where this one is 2.6. Here I get around 3.3. So this is, I know it's also a nicer number, closer to what I want. So these first 2 data points are not actually good data points. Extension students will see that in some further data processing. So we got our graph. I'm going to make sure you save your graph, and let's go down here. Record the value speed for the A value. I have 3.314, which is what I have here. Note E means times 10 to the 4. So I'm going to go 3.314 times 10 to the 4. And I need to make that be a superscript. Superscript. Got research/Google the value of the speed of sounding error and compare that to your value. Critically think and discuss part why your value might be so different. When I Google search the speed of sound, I go to speed of sound in air. Google tells me 346 meters per second. I'm not going to use that number. I'm going to use 343 meters per second. Well, actually, we'll use this room temperature. It's a bit warmer. 346 meters per second. Good. So I'm going to record that. Here, 346 meters per second. I'll get rid of these other lines. I'll just make this red so it's easy for you to see. Oh, these numbers are kind of close. I'm going to write this as a regular number, 3314. 1, 2, 3. Oh, one more and a 0 because I'm 10 to the 4. Yes. Now, the numbers are close, but they're not. They're kind of off by 100. Why could the values be off by 100? This is the critical thinking I wanted you to do. Let's look at our table. They might give us some clues. Our wavelengths are in centimeters. And let's see, this is in meters per second. So our value would actually be in centimeters per second. Again, let's make this red so it's easy to jump out at you. Oh, I need to convert this to meters per second. I'll let you do that. 5, 4, 3, 2, 1, Still waiting. Tricked you. Ha. Okay. So there is 100 centimeters in 1 meter. So I need to divide this by 100. So I'm going to have 331.40. The 0.40 is not the point, so I'm going to say 331. Meters per second. Let's again make this red so it jumps out. I'll even bold it. Why not? Okay, so those numbers are quite similar. So now we want to compare these by calculating the percent difference. So this is an equation. I can just double click this equation. What can I just type in here? I just type right in here. Okay, so you're going to type these numbers straight in here. Experimental value, what I got in the experiment. Which of these two values is experimental? Minus theoretical. Which of these is the theoretical correct answer? Divided by theoretical, the value is theoretically correct. So the first one is what we actually got in the experiment, minus the theoretical number, divided by theoretical number, gets us some number, times 100 gets me %. Write that down. And here is the video that I'm making right now. There's a little linky, and soon it will be there for you. Enjoy.